So we covered the visual inspection by using residuals. We also covered some of the statistics called the EI and the DI. You still need to remember because this lecture we are going to continue from there. EI is the residue, as we talked about from the beginning of the class. That is the difference between yi and yi hat. Okay. And also we have defined a standardized residue Ri coming from EI over sigma hat square root of 1 minus HII. HII is the ith diagonal element from the hat matrix. And we also talk about a version di equal to yi minus yi hat, but with ith data point deleted. Basically, you are predicting the y hat by using the model. The model, actually, when you use the model to fit the data, you have the ith data point removed. And it also has a normalized version, standardized version, called Ri star. It equals to EI versus sigma hat, but with ith deleted and the square root of 1 minus HII. Okay? So compare these two. In structure, it looks very similar, EI versus the sigma hat and the square root of HII. But the difference here is how you calculate this sigma hat, how you calculate this sigma hat I. Sigma hat with ith deleted, basically sigma hat squared with ith deleted. So this one is using the old formula we learned, SSE over n minus p minus 1. Okay, but with ith deleted, you are using the SSE with ith deleted. Even the SSE is not the same with ith deleted. Divided by n minus p minus 2, because you have one fewer data point than this one. That's why you minus 2, okay? This is how you calculate the sigma. And also remember there's a relationship between DI and EI. DI actually equal to EI over 1 minus HI. This relationship, we don't require you to prove, but we just use it. It comes from here. I didn't give you last time, but I think it's okay to give you because this is how you can come to here. So the beta hat, the estimated coefficient minus the beta hat with ith deleted. Okay, use the model to fit the data set, but with ith deleted. There's a relationship between these two, that x transpose x inverse xi, the ith data point, ei over 1 minus HII. This is the formula we just use without proof, okay? Coming from a paper coming from Hoagland, 1978, okay? So this is the star formula. From here, we can derive the formula like this, and we can derive their relationship, all right? So this is the RI is called internally standardized. This is called internally standardized. This RI star here is externally standardized residue. Okay, so what do you mean by what? What do you mean by the ith deleted? In your data set, you have n data point. You have the ith data point deleted from the data set. That's what it means. All right. So today we are going to talk about section 4.8. We'll continue to derive the formula from here. That's why I put it here. All right. So the focus here is how do you use some kind of a test statistic to detect outlier and also high leverage point? What point is influential? What is the high leverage? So first, intuitively, what do we mean by outlier? What do we mean by high leverage? What do we mean by influential? So we have been talking about using the Ri and Ri star to detect outliers. What kind of a property or characteristic does the outlier have? Do you have any intuition here?
An outlier isn't something that you would expect to see in your data. Like it comes as a surprise that it's there. I think a lot of places use the 3 standard deviations rule. So if it lies outside of 3 standard deviations above or below the mean, then that's considered an outlier.
Yeah, but essentially it come from the root. The root is the difference between what the predicted value and observed value, right? The root from all the Ri here is this. No matter is y minus y hat or y minus y hat with isolated, that's the difference between observed and predicted. So what kind of data will have large EI or DI? That is, when you have a regression line, no matter what data, full data or the isolated data, you have a regression line, this data point will be far away from the line, right? So y hat coming from your regression line, y is observed data. Remember what it looks like on the scatter plot. If there's a large difference, that means this data point here is far away from the regression line. The next one would be just use a different model, but still you have a regression line. And then the yi is far away from the regression line. So the outlier, no matter which measure you use, you can use Ri, you can use Ri star. Oh, by the way, what is the reason we introduce Ri star? Why don't we use Ri? Do you still remember? You forget, okay. So the reason here is if some point can influence the regression line, basically pull the regression line toward itself, the difference between y and y hat could be very small. It could go undetected. But if you fit the regression line by having the ice deleted, this point will not be able to pull the regression line toward itself. Okay? And also there's an important reason here. The EI and the sigma hat here, they are not independent. So we cannot say Ri has a T distribution. But with the Ri star, EI and sigma hat with ice deleted, they are independent. And we can have a T distribution. Once you have a T distribution, you can use a standard t-test, right? So that's the reason why we introduced the deleted model. But overall, you including the both Ri and Ri star, the outlier captures extreme values in Y. Extreme values in Y, precisely talking about yi minus y hat or yi minus y hat with ice deleted. Okay. The high leverage point, on the other hand, is talking about extreme values in X. It will be far away from the center, okay? Precisely, it is extreme value in X minus X bar. If it's a simple linear regression, it will be just the distance between these two is the absolute value. If it's a higher dimension problem, you're looking at the 2 norm. Okay, so influential point here, influential point needs to be extreme in both Y and X. If it is not extreme in one, only extreme in the other, it may not be influential, okay? So basically extreme in both Y and X. So that's so basically intuitively understand what is influential point. This point is able to influence what the regression line look like. Adding this point or removing this point will result in a different regression line. Okay, so how do we, this is the intuition behind this. How do we quantify that? We need to have some kind of measure eventually, numerical compute that and use the standard test procedure. That's what we like to do next. So first, we need to have a measure for leverage. So what is a good measure for leverage? The high leverage point is the point that has extreme value in x minus x bar. What do you use as a measure for leverage? We don't just calculate each point x minus x bar, right? So you remember there's a hat matrix. The hat matrix H equal to x transpose x inverse x transpose. Okay, y hat here equal to hy. So we just conveniently define hii, which is the ith row ith column from the hat matrix, is defined to be the leverage. Okay, we define the hii to be the leverage. So how come this actually give you some indication of how far it is from the x bar, from the center? So let's look at what properties this HI have. Properties of HII. One, it quantifies xi minus x bar. So if it is a scalar in simple linear regression, this is just the absolute value of the difference. But if it is multiple linear regression, you get a vector, xi and x bar both are vector. You get the difference between two vectors, then you can calculate the two norm, okay? Second one, it is also a value that between 0 and 1. And the third, it also has the property that the sum of HII, I goes from 1 to n, equal to p plus 1. So because we define HII as the leverage of the ith data point, right? So we define h bar equal to sum of all the HII, I goes 1 to n, divided by n. That is the average of all the HII. It's equal to p plus 1 over n. Okay, this is h. You may not be able to tell h from n from my handwritten note. This is n, this is n. So any point with HII greater than 3 times h bar, you would consider the point I high leverage. Okay. If a data point has HI greater than 3 times h bar, you consider this ith data point high leverage. So if it is not greater than 3 bar, failing that, if HII is greater than 2 times h bar, and also isolated, but basically means other points are clustered, but this one is far away from that. Regardless, high leverage. Okay. If it's not 3 bar, but it has 2 bar, 2 h bar, and also an isolated point, you can consider it as high leverage point. Okay, now let's look at the property, how we prove that. Is that in your homework? If it is in your homework, I should not do it here. Homework 3. It's in your homework. In that case, I give you a hint here, but I won't give you the full solution, okay? It is in your homework. So prove for HII belong to 0 and 1. So you first write based on the definition of H. Oh, you want this sheet? Okay. So you want to show that it is a value between 0 to 1. First of all, you know the H has idempotent property. H equal to H. Okay. Then you can write out what is HII. What is HI? It basically equal to summation of HIJ multiplied by HJI. Then you have J equal to 1 to N. Then you can split that into two sum of squares. So basically you have, because it is also symmetric, right? H is also symmetric. Hij and Hji are equal. So basically summation of Hij squared. Okay. J equal to 1 to N. Then what? This can be split into two parts. Summation of Hij squared. J is not equal to I plus Hii squared. Okay. Now from here, you can talk about why it is between 0 and 1. Okay. I will stop here. Not done yet. Remaining work is yours. So to show that it is, in order to show that summation of Hii, I goes from 1 to N equal to P plus 1. This one just use the definition of a trace, because this is the definition for trace, right? Sum of Hii is a trace. And then use the circular property of a trace, can easily get it. All right, should be not that very hard. I think once you get to this point, the remaining is easy. All right. So next we are going to talk about section 9. There will be some popular measures to measure the influence of data point here. And all these are based on some of the properties, some of the test statistics we defined earlier with different combinations. So measures for influence. As I said, an influential point needs to be both having high leverage and also to some degree have extreme wide values. So the first measure here is called Cook's distance measure. So the Cook's distance measure here, defined as Ci equal to summation. I start to use sub k here because in order to avoid confusing with this I, this measures the i's data point influence. I is fixed. I stay in the formula as a constant. You don't want to mess up. So the yk hat minus yk hat with the i's deleted. So basically, with i's deleted, you have a different regression model. This is with i's included. You also have different regression model. Then you calculate the difference between the two predicted value for the case data point where k goes from 1 to n. Square it, because obviously plus minus doesn't matter. Then you have divided by sigma hat squared times p plus 1. Okay, the sigma hat is the same old as we talked about before. here the sigma hat squared equal to SSE, the full data point, n minus p minus 1, okay? So understand I'm using k here in order to avoid confusing with ice. That's two models with ice deleted and with ice included. But you are going to predict all the data point. Then look at the difference here. So what exactly does Cook's distance measure? We need to be able to understand what it measures, right? So this is the definition. And if the CI here is greater than if statistic with 0.5, p plus 1 degree freedom, n minus p minus 1 degree freedom, and we can consider the ice data point as influential point. Okay, is that 0.5 or 0.05? Let me check what is saying in the textbook. Okay, it is 0.5. Okay, so the reason that I check is because in all the F tests we used before, we are checking like alpha equal to 5%, that's 0.05. But here we are actually check 50% point, okay? 50%, it is not a typo, not a typo. You are checking the 50% point, like 50% quantile of the F distribution. So if CR is greater than that, consider it an influential point. So how exactly does, what does the CI measure here? You look at here, looks like my window is gone, right? Okay, now it's back. You look at what is CI measure. Here, the I is fixed. You basically have the i's data point deleted, then use the model to predict all the y's. Then you look at how much difference is in here. So basically what CI measure is the effect of the i's data point on all the unfitted value. Essentially, you can see the effect of the i's data point on the entire regression line. If it doesn't change much, the CI will be small, right? In that case, it's not influential. But if it changes the regression line too much, the difference will be large. It changes the regression line too much. This difference will be large, the CI will be large, then eventually it will be considered influential, okay? So basically, essentially, CI measures the effect of the i's data point on all fitted values. On all fitted values is also considered on the regression line. If it doesn't change regression line too much, it's not influential. If it changes regression line a lot, it is influential intuitively, okay? So in practice, what if you don't want to look up the table or you don't have the table because this is F distribution? A rule of thumb here is if CI is greater than 1, consider the ith data point influential. Yeah. If you don't want to look up the table, in practice, CI greater than 1 is considered very influential. Okay? Any question for the Cook's distance so far? Did I receive any? All right. So the next measure here is called diff fits. Diff fits. The book has a F left. It only shows one F, but actually it's 2F, okay? It's difference in fits. Difference in fits. You know what is fits? Fits is y hat. Explain what again? Diff fits. Okay, that's 2 words. Difference in fits. You want to explain Cook distance. Which part? So basically, intuitively, the Cook distance, how do you get the ice deleted? When you train the